So we know that AC dynamo generates electricity, right? Now, see, whenever we have current can flow in any direction, right? So direction plays a very important part. So how do we get to know in what direction is the current flowing? So now to know this, we use Fleming's right hand rule. Okay. Now Fleming's right hand rule, what it states is, so whenever we have the first three fingers, that is the thumb finger, index finger and the mid finger, extended mutually perpendicular to each other, then the thumb finger represents the motion of the conductor, the index finger represents the field, and the mid finger represents the direction of the induced current. Okay, so mind you, it's the induced current. So this is Fleming's right hand rule. Now this Fleming's right hand rule is very much required to know the direction of the induced current by the AC dynamo. Okay, fine. So let's start with the working of the AC dynamo. So what we have is, see, this is the armature given. Now you have ABCD, this is the armature. Now AB is on the top and CD is on the bottom, correct? So this is at time t is equal to 0. Now then what happens? So at time t equals to 0 to, let's say, t by 2. Okay, so 0 to t is the total time period. So let's split it into two halves, from 0 to t by 2 and t by 2 to t. Okay. Now from 0 to t by 2 we are going. So in between I'll have one more part, which is t by 4. So technically we are dividing 0 to t as 0, t by 4, t by 2, 3t by 4 and t. Okay, so these are the parts we have. So now from 0 to t by 2 if we are going, now AB is at the top and CD is at the bottom at t equals to 0. Now at t by 2, AB will be at the bottom and CD will be at the top, correct? So while it is going, now at t equals to 0, if we use Fleming's right hand rule, then the flux linking with the coil will be 0. Okay, why it will be 0? Because remember BA cos theta we were doing for magnetic flux. In this case theta will be 90. Okay, that's the reason phi will become 0. So no flux, so no EMF. EMF is 0. Okay. Now as the coil rotates to move, now at t is equal to t by 4. See here, at t is equal to t by 4. Now maximum flux will be linking with the coil. Okay, so maximum. So EMF induced will be maximum. Again, to know the direction, we use Fleming's right hand rule. Okay, Fleming's right hand rule. So then at t is equal to t by 2, the coil rotates, and that means AB is at the bottom, CD is at the top now. Okay, now again it is 0 because theta becomes 90. Alright, next from t by 2 to t we are going. In between we have 3t by 4. Okay, so from t by 2, again it rotates. See, this is the position now. Now again we have maximum EMF, but in the opposite direction. So direction again comes from the Fleming's right hand rule. Okay, so when we are doing Fleming's right hand rule, so remember, see, this is the motion, correct? Right, this is the motion. So when it is rotating, let's say this is the motion, this is the field. Now this becomes the EMF. Okay, the induced EMF. Alright, so that becomes in the negative scale, or it comes in the negative scale. Then from 3t by 4 to t again. See, now it comes back to its original position. AB is at the top, CD is at the bottom. So again EMF is 0. Okay. Now if you look at the whole curve, so from 0 to maximum to 0, negative maximum, 0 again. So this is nothing but a sinusoidal wave, correct? Okay. So this is the reason, this is an alternating current. So we call this as an AC dynamo. Alright. See, now we got to know how the EMF looks like. So we need to calculate what is the magnitude of it. That is, we need to have a mathematical expression for the induced EMF.